Let's continue trying to organize our knowledge. Let's think about the harmonic. Is the original series here, is the harmonic convergent or not? Is the sum of the absolute value terms convergent? Then we can think about the alternating harmonic. Is the sum of the original series exactly as it's written here convergent? Is the sum of the absolute values convergent? And then think about P series. Is the sum as it's written here convergent? Is the sum convergent if you take absolute values? And then think about geometric. So pause the video and go fill out here with yeses and nos, and types would be like absolutely convergent, conditionally convergent, or divergent. And then come back and we'll see what we think of the table. Okay, welcome back. So is the harmonic originally convergent? No, famously the harmonic is not convergent. Is the harmonic convergent if you take absolute values? Well, it's already all positive. Taking absolute values doesn't do anything, so it's not convergent that way either. So what type is it? It's divergent. How about the alternating harmonic? Is it convergent when written in this form with the alternating signs? Yes, it is. We saw that that was equal to log 2, or at least you trusted me. Is it convergent when you take absolute values? No, because then it's just the harmonic. And what do we call a series that's convergent as it is, but not convergent if you take absolute values? That's conditionally convergent. How about alternating P series? Maybe it depends on the P value. So if P is 1, then we're dealing with the harmonic. What if P is 2? Then this series would be convergent. It follows all the alternating series test. So if P is 2, the original is convergent by the alternating series test, and the sum of the absolute values, that's just the sum of 1 over n squared, that's also convergent. So there's a yes. So let's do a kind of subset here. Not just p equals 2, but really p greater than 1. What if p is less than 1? So if it's originally convergent and the absolute values are convergent, then that's absolutely convergent, right? What if p is less than 1? Does this still meet the alternating series test? Yeah, it does. If p is like 0.5, 1 over n to the 0.5 is still decreasing. It still has a limit of 0. So the original would be convergent, but the sum of the absolutes would fail the P series test. So that would be conditionally convergent. And then for geometric, what did you end up saying? Maybe it depends on the value of r. So let's list some possible values of r. If r is bigger than 1, then that's like 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. That just runs off. So it's not convergent originally. Taking absolute values is not going to help adding up exponential growth. So this is just divergent. What if r is less than 1? Oh, we didn't say here, should we have an equal sign here or an equal sign here? Like if p equals 1, which category should this go in? Well, if p equals 1, that's harmonic or alternating harmonic, which is originally convergent but not absolutely convergent, so the equal sign would go here. What if r was equal to 1? Then we would just have 1 plus 1 plus 1 plus 1 plus 1. That's just going to diverge, so we can say r greater than or equal to 1. What if r is between 0 and 1? That would be like a half plus a fourth plus an eighth plus a 16th. That converges. Does that converge if you take absolute values? Yeah, it's already positive already. So that would be absolutely convergent. What if r is between -1 and 0? That would be like positive a half minus a fourth plus an eighth minus a 16th. Is that going to converge? Yeah, we know the geometric converges even when you have those alternating signs. Does it converge when all the numbers are positive? Yeah, we were just on the previous row there. And then what if r is less than -1? That would be like -2 plus 4 minus 8 plus 16 minus 32. That's just going to keep oscillating, getting bigger and bigger. So that does not converge. If you take absolute values, you're just going to get a huge bunch of positive numbers. So that's going to be divergent. So those are our main types of series. So let's go organize those in something like the Venn diagram we had before. So we'll have divergent series here, and then we'll make like a thick bar and have conditionally convergent series here, and then a not so thick bar and have absolutely convergent series here. So you can kind of diagram, so this side of the double bar is convergent, this side is divergent, but conditional is kind of closer to divergent, because if you take absolute values, then it becomes divergent. So that's why I have them in this order and not the opposite order. So we can say harmonic goes in the divergent category. Alternating harmonic goes in the conditionally convergent. And then alternating p-series, we said alternating p-series with p less than 1 is conditionally convergent, p less than or equal to 1. And alternating p-series with p greater than 1 is absolutely convergent. Alternating harmonic is part of alternating p-series with p less than 1, so that's actually kind of the same thing. And then for geometric, we could say geometric with, oh, we forgot, if r is equal to -1, then we just have +1, -1, +1, -1, +1, -1. It oscillates without settling down, so that would be divergent. So we'd say like that. So geometric with absolute value of r bigger than or equal to 1 would go here. And if r is between plus and -1, then that's absolutely convergent. So it looks like geometric series are never conditionally convergent. They're either absolutely convergent or divergent. So that's kind of a picture of our landscape of favorite series. One quick question. We saw rows here that said no, no, yes, no, yes, yes. We didn't see any rows that said what? Said no, yes. So back up here. Originally convergent, no. Absolutely convergent, yes. So we didn't have any rows up there that said that, but is that possible? Take a sec to think about that. Well, we know that if a series is absolutely convergent, then it's convergent when you throw in the pluses and minuses that it originally had. So if it is absolutely convergent, then it must also be originally convergent. So absolutely convergent forces it to be originally convergent. Or you could say it can't be absolutely convergent unless it's originally convergent.